Good afternoon, everyone. Before we get started, are there any questions about the midterm on Friday? Everybody's good? Okay. I think today will be a short lecture. Just had a few examples of how you do generative AI, and just wanted to go through those. And in some sense, these are just architectures or buzzwords you may have heard of, so I just wanted to describe a little bit about them. So the first is autoencoders and variational autoencoders, VAEs. So these networks have an architecture like this, where you take in something like an image, you go through an encoder, and the encoder squeezes the input down so that the number of dimensions here is smaller. So, maybe you have a 100 by 100 image, and maybe you come out of here and you have just 100 coefficients total, for example. And those things in the middle are called Z. And then there's a decoder that takes those few Z's and basically tries to recover this image X. The approximation is called X prime. And so for some data set, for some training data set that you have, you train the encoder and decoder so that together they try to preserve as much about X here into X prime. And so you would imagine that there's probably going to be some loss in doing so. If you have an image and you're trying to describe that image with, let's say, 100 numbers, then how can you describe an image with 100 numbers? That's not enough. But if you have a very sophisticated encoder and decoder here, it is possible perhaps to describe some subset of images. So examples of this that are pretty common in the literature would be faces. So there's these face data sets. And you might say, well, okay, so how many different faces are there? So, maybe there's certain things about faces in addition to the shape of the face. There's the lighting and there's the orientation and so on. But you can train these things to do pretty well in terms of taking in a face, representing that with a few numbers, and then generating that face again. Now, if you take that autoencoder that's trained on faces and you put in some other kinds of images, generally it won't work well because it's really just trained to represent faces with a few numbers and then generate faces from those few numbers. And that discrepancy is actually possibly very useful. So when we talk about the applications of these things, the first application, maybe the most obvious one, is you can think about this as doing some sort of compression. So you want to be able to describe faces with just a few numbers so that you can maybe just store those numbers instead of storing the whole face. And then when you want to reproduce them, you just put them through the decoder. But given that this network has been trained to code and decode faces very well, but is not going to work well with other signals, you can actually use that to your advantage. So if you want to do denoising, meaning you want to take a noisy face and somehow remove the noise, it's maybe sort of intuitive that this encoder and decoder trained on clean faces. Clean faces are quite structured. When you think about a noise image looks extremely random. Even when you add noise to a clean image, that image becomes much more random. If you take that noisy image and you put it through here, what comes out is not going to have much noise in it because this decoder doesn't really know how to make noisy faces. It was only trained to make clean faces. So the noise will change this code vector a little bit, and it will increase the difference between X and X prime. But if this is a really good encoder-decoder pair, this should look like a clean face that's just, the closest clean face to this noisy face here. Okay, so that's how you can use this thing for denoising. Another application is anomaly detection, where you have, let's say, again, we have a data set of faces. We trained our autoencoder on faces, and now we want to detect if a new image is a face or not a face. So we would imagine that this encoder-decoder network is going to be pretty good at preserving a face. So if I put in a particular face here, I should get something very close to that face out. But if I put in something different, like a cat, which looks, this decoder it's never been able to generate a cat. It's never trained to do that. So it will generate some face that looks, maybe somehow close to the cat you put in. But if you look at the discrepancy, the difference between x and x prime, that will be very large for the cat and very small for faces. And so you can use that to detect whether something is anomalous with respect to the training data or not. So that's another application of these things. And then a final application would be generative modeling. So the idea here is with a large data set of faces, you train this thing, encoder and decoder, to do a good job preserving those faces. And now you just forget about the encoder and you stick in random noise, Z. And if this decoder is only able to generate faces, then you just put in different random noises and you get out different random faces. And so that's an example of generative modeling when you use this part as a generator. Okay. So any questions on those applications or ideas? No? Okay. So an improvement on these encoders, autoencoders, are the so-called variational autoencoders. So what they do is rather than the encoder outputting this vector of numbers, which you can think of maybe as almost like random numbers, it instead generates statistics, a mean and a variance, from which you can take let's say, white Gaussian, random Gaussian vector, scale it by the mean, each element by the mean in this vector, shift it by this is the standard deviation. So you can scale epsilon by the standard deviation, and then you can shift it by the mean, and that is how you can construct a z. So rather than going directly from here to the z, this is actually generating these statistics from which you can take a new random vector, combine it with the statistics to push it through here. And the VAEs, generally speaking, work much better than these autoencoders. And these guys are actually they work relatively well. So in terms of how you train this, there's a few things that you want. So on the left here, you can kind of see this. This is the idea of taking in this vector of zero mean, unit variance, independent Gaussians. This is an element-wise multiply, so you're multiplying that by the particular vector of standard deviations that the encoder output for a given input xi. You're then shifting that with the means that the encoder output for that xi, and you're taking that new code vector zi, putting that through the decoder, and you want that the output of this is as close to the input xi as possible. So that's what this term is doing. It's just looking at the squared error. But then you might want something else. You might want that that the Gaussians, so this is like a Gaussian with a particular mean and standard deviation. You want that maybe these Gaussians look close to zero mean, unit variance Gaussian on average for all your training images. And one way to do that is to use this KL. This is the Kullback-Leibler divergence, which is a way of comparing two distributions. And it's saying that you want this Gaussian with this particular mean and variance to be close to this Gaussian with zero mean and identity covariance. So this is This is an extra term that you can add to prevent these things from being too far from 1 and 0. So this is the typical training cost, the thing you optimize. These theta and phi would be the parameters of the encoder and the decoder, respectively. So those are VAEs and autoencoders. So any question on those? How many of you guys have heard of these VAEs or autoencoders? Okay. Nobody. Okay. All right. So what about GANs? Have you guys heard of GANs? Okay. So a GAN is similar in spirit to this part. It takes in some random, usually Gaussian, zero mean, identity covariance, random Z, puts it through a network that expands that and generates some sort of images from a set that you want. So again, we could say faces. Put in random Gaussians, outcome faces. And so with the GAN, the question, or the difference is how you train this. So here with the VAE, the training is, you're sort of just focusing on the square error. The trouble with squared error is that squared error as a metric, as a way of training, does not give you sharp images. It gives you kind of blurry outputs because squared error doesn't really care about edges that much. And so if you want to do better, you have to change the loss. Squared error is not going to be good enough. So there's a very clever idea of rather than using squared error, you have another network called a discriminator. So this is what we just talked about. Design the generator to map a latent vector Z to the X domain. The new thing is design a discriminator, which is another deep network, that is essentially just a classifier of whether X is real or fake. If it's a real image, like from a data set that this discriminator is aware of, the discriminator is going to give a big number, maybe let's say close to 1. And if X is a fake image, meaning it was generated from this generator over here, then the discriminator should notice that this is like a fake or counterfeit image, and it should give a small number, let's say close to 0. So now you have a generator that's trying to be, you could say, a good counterfeiter, and then you have the discriminator that's trying to be a detector of these counterfeit faces. And you train them together. So when you start, they're both pretty weak, but gradually the generator starts to fool the discriminator more and more, and then the discriminator learns how to be sort of an expert for that generator, and now that becomes really good, and then the generator gets better, and they sort of as a pair keep getting better and better and better until the generator is quite good and the discriminator is quite good too. And by doing this, you can generate some very sharp, very realistic faces. Sharper, more realistic than with the VAE. So the image up here just shows on the left, maybe these are examples of the training set of XIs that you're starting with. These are things that the discriminator during training has access to, whereas the generator is able to create these. So these are no real faces of anyone in the world. This is just stuff that this generator was able to take a Gaussian covector and warp it into these. And that's how the GAN works, essentially. So you jointly train. So typically what that means is you iterate. So you do one training iteration, you improve the generator. Next training iteration, you improve the discriminator. So you just alternate between them. When you train so there's a separate loss for each one. So when training the generator, this is the loss. So you take this random code vector, you put it through the generator, now that's an image. You put that through the discriminator, now let's say that's a number between 0 and 1. From the generator's perspective, it wants the discriminator to output a large number because it wants the discriminator to think that this is a real face, not something that this generator generated. And so it wants this to be large, so that means the log is also large. But because this is a cost, we'll put a minus sign on it because we want to minimize the cost or maximize this. So that's the generator's objective. It's trying to maximize this. The discriminator has kind of the opposite objective. For the discriminator, it wants that for all the true training faces, if you put them directly into the discriminator, these should be large because they're real. But because it's a cost, we're going to make it negative so that we can minimize this. However, for that discriminator, it wants that if you take Z, put it through the generator to get a clean face, a fake face, put that through the discriminator, it wants that thing to be small. So it wants 1 minus that to be large, or log of that to be large, or this again minus sign is because this is a loss. So this is the loss you use when training the generator. This is the loss you use when training the discriminator. Alternate back and forth in really good results. So these are a number of the, I think these were first proposed around, 2015 or so. And they basically over the years got better and better and better. All right. Any questions on GANs? Okay. All right. Normalizing flows are a little bit more modern. So normalizing flow, this part of it looks like the GAN sort of generator architecture we just described. So you're taking in noise, you're putting that through a network to get, let's say, faces. On the left side, it looks just like the encoder in our VAE or maybe the encoder in our autoencoder. So you take here a face, put it through this network to get the code vector. Now what's special about these normalizing flows are that the neural network that is used is invertible. And so in fact, this and this are the same network. It's just that in one case, you put the data through one direction, and in the other case, you put it through the opposite direction. And because this is an invertible network, putting it left, putting it right are just the inverse of the other. So creating an invertible network is not exactly easy in that there's a lot of constraints. You can't just put in a conv layer, put in a ReLU. ReLUs are not invertible, right? ReLUs, like when you set when we set all negative numbers to 0, you can't go backwards and get them back. So there's a lot of constraints when you do this, but there's actually even more constraints, as I'll describe in a moment. But basically, the way that you train these things is, assume that you have this invertible neural network. You have a bunch of data. You train this part so that as you push real faces through this thing, you try to make the outputs as close to 0 mean unit variance Gaussian as possible. So that's what you do during training. You just work on this part. Try to map faces to Gaussians. So they're called normalizing because you're trying to make this normal random variables. Once this thing is trained, because it's invertible, you can just put data in backwards and take new 0 mean unit variance Gaussians, put them backwards through the network, and out come faces. So that's what's cool about it. And in particular, what makes it maybe the advantage you get over these GANs is that training it, you don't have this complicated discriminator network and all that. You can actually use maximum likelihood to train this. And it all boils down to this, this one equation, which has two parts. So here's the log of the product over the data samples in our training set of this term. This term here on the left says if I take a face, put it through the inverse network, we want this thing to be Gaussian. So in some sense, you would expect the likelihood to just be, okay, here's the code vector for that face, here's the PDF. And so this is the likelihood. But there's another part of it, which is to say that you want, when you go through the math, whenever you transform a random variable, sort of like in calculus class when you learned about, with an integral, if you want to do a variable transformation in an integral, there's this Jacobian term that pops up that you need to put in there to make sure that you get the same value. When you transform random variables, it's the same thing. Transform one random variable to another, there's the Jacobian of the transformation has to be applied to the density to make sure that everything integrates to 1. So here is the Jacobian. So this is a matrix. This is the Jacobian of this guy. And then here we have the determinant of the Jacobian and just the absolute value of the determinant of the Jacobian. So this is sort of how the likelihood manifests. So this is just the thing we want to minimize. Theta would be the parameters of this neural network. The same parameters, of course, govern the inverse network because it's really the same network. And so now the challenge is, in order to train this efficiently, you need that, not only does the network have to be something you can evaluate, but the inverse has to be something you can evaluate efficiently, as well as the determinant of the Jacobian of the inverse. All those things have to be computationally efficient for evaluation. And so over the years, people have thought of very clever ways to make neural networks where all these things are tractable, efficient to compute. Although there are, of course, limitations. You can't just stick in your usual convenant in here. It doesn't have tractable determinant Jacobians or inverses. But there are classes of neural networks that do. And that's how you get these normalizing flows. The cool thing about once you have this flow trained is that given any new sample, X, you can plug it in and immediately tell what is the log likelihood. So coming back to things like anomaly detection, if you train this on a set of training samples, and now you have a new test sample and you ask the question, is this test sample likely or unlikely to have come from this training distribution? Well, you can just plug it into this likelihood expression directly, and you can say, does this sample, if I plot a histogram of likelihoods for my training, is this kind of right in the center of that histogram, or is it an outlier? If it's an outlier, if it's not, doesn't behave like the rest of your training samples, it's probably different than them. It's anomalous. So that's a way of doing anomaly detection with these normalizing flows. Okay, so that's so the quality of these, I would say, is on par with GANs. Just a little bit more modern of an idea, and the training is more stable than a GAN, but the downside is there's more restrictions on how the architecture looks because of these constraints. Okay, so that's normalizing flows. Any questions on those? All right. The thing that's really hot these days are diffusion models. So diffusion models, in one sense, they're very similar to a lot of these techniques we've talked about. So okay, so on one sense, the way that they work, when you're actually applying them, goes like this. You start with, again, a Gaussian, random Gaussian noise image, and you map it to a face. So this is exactly what happens here. It's also exactly what happens with GANs as the generator as well as here. So they all have that in common. What's different about diffusion models is that this is actually done in many small steps. So to go from here to here, there's essentially a neural network. So whereas in the normalizing flow, this is, you could say, done in one step, there's one neural network that takes you from noise to image, or noise to face. Here, you have a bunch of small steps that take you from noise, pure noise, to almost pure noise with a tiny little bit of a face in there. And then the next neural network, slightly less noise, and eventually, after you do about 1,000 steps, you get a clean face. So now if I would have started with a different random sample here, I would do this, I would get a different clean face. So this is how it's sort of generative. The way that you train this is what's sort of remarkable. The way that you train this is you start with a database of clean training faces, and you add a little bit of noise to that face to get you this. And then you add a little bit noise again, slightly noisier. So this direction is super easy. This is what's called the forward diffusion. You start with this original image, gradually add noise over t steps, and the conditional distribution from x at step t to x at the previous step just looks like this. So here's the new x, here's the old x multiplied by a number slightly less than 1, but you're adding to it a little bit of Gaussian noise. There's a couple ways to do it. This way just ensures that the overall energy from x minus 1 to xt minus 1 to xt is the same. There's another version of this where you don't have this scaling and you just add noise. So this is add noise and slightly reduce the amplitude a little bit so that overall the energy here and the energy here are the same. But anyway, this forward diffusion is very easy. You just add noise in many small steps. What's more complicated is the backward diffusion. But the backward diffusion is based on the idea that it's not too difficult to design a network that just removes a little bit of noise. So every one of these steps, we have a neural network that just removes a bit of noise. And then that same network, but with you actually give that network this number t. You give it a new t, which says, okay, I'm giving you slightly less noisy input, so that it knows how noisy it is, and then you just ask it, okay, remove just a little bit of noise from that. And because this network has a relatively easy job to do, which is just remove a little bit of noise, it can do it really well. And so the cost of this is that, well, you have to put it through a network 1,000 times. But the results you get are super good. And so a lot of these really cutting edge image generators are based on this idea of diffusion. So this is something that's more computationally expensive than these other approaches, but if you have that ability to run that, usually that runs in some server farm, then it can give you really good results. Also, in general, the way these cutting edge models are trained is they're trained with billions of images. So the training sets are massive, but the results are really, really good. Okay, so far we've just talked about how you work with images alone. So take a set of training images, you gradually add a little bit of noise, and then learn how to go in the backwards direction. What's more interesting is that if you don't work just with images, but pairs of image and text. And when you work with pairs of images and text, it allows you to exploit something called conditional diffusion, which is all this diffusion stuff, but it also involves conditioning. And what you can then do is you can say, okay, conditioned on the text being this phrase, I want you to generate an image like this. And this is how you get a lot of these things where you give it this phrase of text. This is you're kind of conditioning on the text component of this joint text image thing, and then you use diffusion to gradually, from noise, gradually remove the noise until you get an image like this. And these are just all different examples of putting in this text phrase and getting out, pretty remarkably, an image that perfectly describes that text phrase. So Pretty cool stuff. So that's, any questions on these diffusion models? Okay. That's all I had prepared for this unit. Are there any other topics that you wish I would have talked about here for deep learning? Because actually this is it for deep learning as well. We're going to move on to talk about trees in the next unit, random forests, things like that. And then after that, we're going to talk about clustering. We'll talk a bit about working with text data. And we'll talk about PCA, non-negative matrix factorization, a few other topics like that. But this is sort of going to be it for deep networks. So yeah, what things have I not talked about that you were hoping to learn about? Anything? Yeah.
I'm curious about like models that use videos.
Videos, okay. Yeah, so on one level, handling videos is not really that different from handling images. Images are 2D objects. Videos, you just add a third dimension, which is time. So instead of a tensor that's two-way tensor, you have a three-way tensor. Instead of 2D convolution, you have 3D convolution. So you can just build the convolutions just exactly like we described, but with 3D convolution in them. You can build, so that would be if you're doing, let's say, classifying videos. Now let's say you want to, denoise a video. You can build this unit, but instead of 2D convolutions, you have 3D convolutions. So the extension is not that different intellectually. Computationally, you have to have more processing power. Another issue with the videos is there's less videos than images out there to use for training data. So it's kind of an issue too. But it's definitely something that people are working on a lot. So in fact, for like generative AI videos are what currently people are doing a lot with that. And so put in a text phrase of a video now, like within the last year, they can just generate a video that matches the text phrase. And it's, again, based on this. It's like diffusion models. The ideas are all the same, but now you're working with 3D things, and there are a few tricks. So this idea of the autoencoders has come back, and when you talk about, maybe you've heard about latent diffusion, it basically means that instead of working with the whole image, which has a lot of pixels, or the whole video, which has a lot of voxels, you instead encode it into a much smaller dimensional representation, and you work with that. So you train all the networks in this domain, work on smaller data. They can exploit the structures that you have in that data, and then when you're all done, you come back to the full video domain with the decoder. So that is how they get around some of the computational aspects of video processing with these modern networks. So yeah, that's kind of like what I would summarize in terms of video processing. All right. Another question? Yeah.
I was going to say, are language models also using the transformers?
Yeah, so transformers, right. So I was curious if someone was going to say that. So the transformer is a different kind of architecture that we haven't seen. It doesn't use any convolution. It uses conceptually something called attention. The idea is that if I, okay, so the idea with convolution is that there's sort of local correlation. If I tell you, here's a pixel, convolution, the whole idea is that is sort of processing local pixels around the point because the kernels tend to be pretty small. Convolution is also, we talked about the idea of what happens, there's this spatial invariance. So what happens in one part of the image, like statistically over many images, tends to happen in other parts of the image. Those are the ideas that convolution obeys that are critical for a lot of image processing. Whereas we saw that convolution allows you to escape the massive computation of full matrix multiplies. Like if you had a matrix that took in a full image, processed it, reproduced another image. Let's say that image had 100,000 pixels, that would be 100,000 by 100,000 matrix, which has 100,000 squared coefficients, which is just impossible, right? So you replace that with a convolution matrix, which only has as many coefficients as your kernel does. So tiny number of coefficients. But now it still respects spatial invariance as well as this local processing that is really good for images. The trouble is once you start working with something like text, text doesn't work that way. A sentence, yes, there's local relationships between words, but the subject and the verb and the object could be in different parts of the sentence. And depending on the way you say the sentence, you could be reversing the order. So when you talk about like what is the structure of sentences, how do I do text processing, convolution just doesn't work well. And so way back when people thought about, excuse me, what are different architectures to handle this? So one idea was this recursive neural network, which maybe it had some convolution, but then it sort of put data through it over and over again to try to do something more with that. And then they had these LSTMs, which are kind of like these recursive neural networks, but work much better over a longer phrase. And they were trying this with text. It still wasn't that great, but then someone had this breakthrough with transformers, which is a completely convolution invariant architecture that instead tries to find relationships between different parts of a vector, different terms in a sentence that could be anywhere, and sort of responds more automatically to what it's seeing. And so the downside of this is that computationally, at least in its basic form, the complexity grows quadratically with the length of the number of coefficients. So convolution doesn't work like that, but this does. So there's various ways in which people try to get around this. But part of it too is that nowadays, like the computation that is available to people, even compared to 5 years ago, is dramatically more. So some of this is just done with just raw processing power. But the big breakthrough with attention is that it gets around convolution and the limitations of convolution. It's much more flexible. But the disadvantage is computationally it's more intense. But anyway, yes, that is kind of like today's architecture that people use with sentences and so on, with text processing. And it allows you, so a transformer sort of allows you, in some sense, to you could build this sort of a structure here with a transformer, where the transformer is used to take a sentence and extract from it the meaning of it, or somehow represent that meaning. And then, for example, this could be the decoder that takes the meaning of that sentence, but in a new language, maps it to the meaning in the new language. And so as you go from one language to another, like the relationships among words as well as the words themselves and everything, the whole grammar changes. But transformers are good with that. They're able to understand those very complex relationships among words in a sentence, and able to learn that from a big, text data set. So maybe next semester I can add a slide, a little more detail on how exactly they work, just to see the actual architecture of them. But that's kind of why I'm asking. I'm curious what do people want to hear about here. But there's, if you're interested, there's lots of good short tutorials and blog posts and stuff on transformers. And the goal of this course is to get you the language and the ideas to the point where you can just go and read that and it makes sense, in a way that wouldn't make sense if you haven't taken this course. Because the ideas are the same, the details differ. what other things are you guys interested in that you would like to know about? Anything?
Yeah, so I think like where you have, let's say the thing, like try and play a game and it plays against itself.
Okay.
It just gets like superhuman.
Yes. So that is reinforcement learning. Reinforcement learning is a branch of artificial intelligence which basically involves some sort of feedback, a sort of feedback that we have not seen at all. We do have a course in reinforcement learning that is offered, it's supposed to be offered every year or used to be co-taught by Industrial Systems Engineering at ECE, but then the faculty, just this year, she left. So now ECE is taking it over, but we may, I can't remember when the next offering is, but it is offered somewhat regularly if you're interested to take the course. But basically, you're exactly right, that somehow like in the framework that we have been working with, you just have a set of training data, an objective, and you train this network or whatever to do the objective. But there, it's like you go beyond that and you sort of imagine that there's like a state of the world, and there's an objective that depends on the state. And the state of the world could be, for example, like the location of all the pieces on the chessboard. And the objective is to eventually to win the game, but maybe like you could measure the objective by how many of the opponent's pieces are on the board. And you want to sort of say, okay, if I'm in a given state, what is the neural network that is going to predict for me the move to make that maximizes my objective, which is reducing the opponent's pieces on the board. And so now the difference is that when you make that move, you actually go to a new state too, right? So not only is your objective changing, but I'm going from the current state to the next state, which is the way the pieces are after I make the move. And that state itself, there's good states and bad states, right? From the perspective of what's going to happen in the game. So maybe you don't want to take their pawn if it's going to give them a checkmate on you. So this branch of machine learning it sort of deals with like a dynamical system. Like the state you're in, it has an objective, but then it has to say, okay, if I make this move, what's going to happen with my state as well as my objective? And you sort of imagine training this to look ahead. Like if I kept doing this, if I kept iterating this state to the next state to the next state, like what's going to happen over time? So that's a bit how you think about reinforcement learning. But that is a branch that we won't talk about, but you can actually take a course at OSU on that. So, any other specific questions or?
Nope.
Okay. Yeah. Great. Anything else? Okay. So I guess that's it for today then. And so Friday is second midterm. Next week, we'll get into trees. And then trees is the last component for your final projects that we haven't talked about. We should be able to cover the tree unit in 2 lectures. So at that point, everybody will have everything they need for the final project. And then so this unit 9 is the last unit that there will be homework and lab on. After that, no more homeworks, no more labs, but there will be quizzes. So, all right, see you guys on Friday.